I am very happy to be here one more time in Lumini, always my favorite place. I wanted to talk about phase transitions in one dimension, sort of to present overview of what we can do now. And hopefully it got inspired people to do maybe similar stuff in higher dimensions. So I will try to say something about statistical physics, but my understanding is very limited. So one would kind of observe a phase transition if you follow evolution of a system, and depending on some continuous external factors, and all of a sudden some kind of change, drastic change in properties of the system happens. And it's a fundamental goal in statistical physics to understand the mechanism of those phase transitions, and I think we are quite far off from that. So what we try to do, we try to study phase transitions using thermodynamic formalism. So we look at potential phi. So this is exactly the potential Jean René was talking about. It's just a continuous function from my shift space x into real numbers. And we define the topological pressure of phi using the variational principle. So this is a supremum of the entropy of the measure mu plus integral with respect to the measure mu, and my measure runs over all shift invariant probability measures. So let me try to give you my very limited understanding of correspondence with statistical physics. So this quantity that stands here, let me get a hand of the pointer. So this one is supposed to represent a minimal, a free energy, negative free energy of my system in a state mu. So the pressure actually minimizes the free energies. And once your system reaches this minimum, it's in some sort of equilibrium. So the measure which realizes the supremum is the measure which minimizes the free energy, and it's called an equilibrium state of phi. And for us on shift spaces, at least one of them exists, doesn't have to be unique. So what we want to do, oops, here you go. So one way to change an equilibrium of the system is to change temperature, let's say. So we introduce a parameter, T, which is the one that was beta in Jean René's talk. For me, it's going to be T. Maybe I will explain a bit later why I changed in the middle. Like my first paper was still with beta and the last one was with T. And I will explain exactly why. Anyway, so this parameter T is the inverse temperature of the system. So when we freeze the system and the temperature goes to 0, my parameter T will go to positive infinity. So again, the temperature changes, equilibrium state changes, and the phase transition should be something where the qualitative change occurs. And intuitively, it means that we want to have two equilibrium states at the same temperature. Okay. Yeah, this is what I just said. So our main tool would be the pressure function. So this is a function that maps T into the topological pressure of the potential T phi. So what is the connection between the regularity of the pressure function and the coexistence of the equilibrium states? So this goes back to the classical result by Walters. he proved that if your topological pressure as a functional over continuous potentials is Gateau differentiable, then this means that at phi, right, at a potential phi, that this means that phi has a unique equilibrium state. And there are consequences from that for our pressure function. You immediately see that if my pressure function is not differentiable at t, this means that the pressure functional is not differentiable in the direction of my potential phi, which means it's not differentiable, and we get that the potential T naught phi has at least two equilibrium states. Now, backwards is not true. Non-uniqueness of equilibrium states does not imply non-differentiability, and the first actual example of this in symbolic settings was given quite recently by Lepladieu, who should be here. Maybe? No? Oh, yes. All right, so he built a continuous potential phi on a mixed subshift of finite type, where the pressure is analytic, but at 2 points on that interval, he has two equilibrium states. So uniqueness of equilibrium states fails. And I actually will give you a picture of the shift because I really enjoyed that picture later on. Okay, so backwards is not true. What is actually true is that non-differentiability of the pressure function at a point T naught is equivalent to the fact that potential T naught phi has two equilibrium states with distinct entropies. So this is kind of something one would expect from a really strong phase transition. You have coexistence of two equilibrium states and they have two different entropies. So we have a sort of classification. Well, not classification. We have various types of phase transitions. So the first order phase transition is the one I just described, correspond to the points of non-differentiability of the pressure function. We have coexistence of equilibrium states with different entropies. We can also look at higher order phase transitions. So these are the points of non-differentiability. These are the points where pressure is differentiable, but not analytic. So at some point, differentiability fails, which might not have different equilibrium states, but still there is some kind of change in the properties that one can see. Now, another type that we saw the example a bit earlier, when we have analytic pressure function, but still multiple equilibrium states. And last but not least is a freezing phase transition. So now for some positive temperature value, right, your system reaches, I shouldn't say unique. We decided it's not. Sorry about that. So it reaches a ground state and ceases to change. Okay, so these are my types of phase transitions. Now, in one-dimensional shift spaces, we have this very powerful result of Roelle for Hölder potentials. So Hölder potentials correspond to exponentially decaying interactions in statistical physics. So not finite range, but exponentially decaying ones. And Roelle proved that on a mixing subshift of finite type, the pressure functional is actually analytic on a space of Hölder potentials, and the equilibrium state is unique. The consequence of this is that when the potential is Hölder, the pressure function is going to be analytic. For each t, t phi has a unique equilibrium state. So there are no phase transitions of any kind. And to to study phase transitions, we have to look at the continuous potentials. So for Hölder potentials, there is nothing to study here in terms of phase transitions. So from now on, our questions are what happens for continuous potentials, and what are those questions? So we are interested to know whether there are any restrictions on the possible number or frequency of phase transitions. So how many are there? How often can they happen? Another question is whether any types of phase transitions can occur for continuous potentials. What is the shape of the pressure function after a transitional value? And finally, what is the behavior at zero temperature? So I will try to answer most of these questions for the continuous potential. A bit of history before. So the first study of phase transitions in symbolic settings, as far as I can tell, was done by Lopez in a series of papers in the 90s. So he built a family of potentials on a full shift onto symbols, which exhibit first order as well as higher order phase transitions at a value T0. And his inspiration was the previous work of Hofbauer. There were a lot of examples here. And in fact, the potentials I'm going to show you are now called Hofbauer potentials. So the exact definition is really not important here, but what happens, so this is the point in the shift. This is the sequence of all zeros, right? So you look at the distance from your x to the point of all zeros, and you define a potential depending on this distance. So when x is 0, your potential is just 0. And when x is away from 0, starting to go away from 0, your potential starts to decay. So it kind of looks like that. It is 0 at 0, and then it goes down. So the Lopez evaluated to some degree, not exactly, a pressure function for his family, and the pressure function looks like this. So you have convex part, and then at this point T0, the phase transition happens, right? And after the point T0, this is in fact that freezing phase transition that Jean-René was talking about. So after the point T0, you have equilibrium state, which is just a point mass measure at 0. And what Lopez proved is that for this family, two behaviors at point T0 are possible. One of them is when here you have two equilibrium states. Exactly, so there is a little corner kind of here. The pressure function is not differentiable, and you get a first order phase transitions. But also for some different values of gamma, you can have just one equilibrium state here, and the pressure function is differentiable, but it's still not analytic. Okay? So what was his methods? So to show that we have uniqueness here, he used the Royal-Perron-Frobenius separator technique, and to show that we have two equilibrium states here, he actually used direct estimates on the pressure or topological definition of the pressure. And because the potentials are kind of very explicitly defined, he could get the estimates from the definition of the pressure and get the result. Okay, and here's another example by Le Pradeux, who studied also some parametric family of potentials on this subshift of finite type. I put a picture here from your paper. I think this is kind of I don't know, very cool picture. So this was a subshift. I'm not going to define the potentials on them, but the phenomena that he observed was the following. So we can have 2 points with higher order phase transitions. We can have the pressure function being strictly convex after the transitional point, so not linear, like in half-power case. And the last one, that we can have analytic pressure functions, but 2 equilibrium states coexist. So these 2 phenomena were observed for the first time on symbolic systems. Okay. Now,
what's the regularity of the potential?
they're continuous, right? They're not Hölder, but they're continuous. So you can talk about modulus of continuity, right? But I don't know exactly where it stands. It does depend on the modulus of continuity, what happens. Okay, so the first order phase transitions. In a joint work with Anthony Quaz and Christian Wolff, who is here in the audience, we looked at the possible number of phase transitions for continuous potentials. So we proved that if you have any increasing sequence of the temperature values, remember this is my temperature, which are T's and not betas. So you pick any increasing sequence which bounded away from 0, and you can find a continuous potential on a shift on 2 symbols, which has first order phase transitions precisely at those points. So our idea is, okay, here it is. So we wanted to build a potential phi so that its equilibrium states sort of move along a sequence of disjoint subshifts. And the subshifts that we pick are the ones we could control. So those are very simple. They're generated basically by 2 words of length 2 to the n, concatenated freely with each other. So these are simple shifts, and then on each of those, my potential will be a constant. So the equilibrium states at phase transitions that we are looking for would be the measures of maximal entropy on those shifts of finite type. What we need from those from the setup is that the pressure of the potential on xn at Tn is the same or than phi of xn plus 1, so the pressures kind of match up at a point Tn, but if you look at any other point that is not Tn or n plus 1, then the pressure is smaller. So we kind of carefully arrange this situation, and the idea is that after that we want potential to kind of sharply drop down outside our subshifts so that all other equilibrium measures don't really contribute anything to the pressure. So I want to give you a picture of this, maybe. Let me do a picture. Here it is. So, so this is my subshifts. Here, they're kind of getting smaller because the entropy is getting smaller. And on each of them, we get constants. And then in between, potentials sort of drop. So we define potential using phi n's. So I think of this as, again, as a kind of a Hofbauer type of potential. It is a constant on xn, and then it drops. And my phi will be the supremum of it. So what was the main difficulty of the proof is to make sure that this, well, other than the potentials that we got, right? So to make sure that this drop is kind of steep enough, so whichever measure I take, which is supported somehow, maybe outside of all those kind of subshifts, so my measure may be supported here, but if I take the integral, the free energy of this measure, it must be less than the pressure. Okay. And our method was different from the one that was before. So the way we estimate the free energy of the potential, we kind of need to figure out the distance of every point x to all of my points xn. So we split each point into sort of blocks. Each of them belongs to one of the xn. And we use that information to estimate phi. How do we store this information? And this is a really new kind of technique that we introduce. We use a pin sequence space. So we have a product of my original shift with z, and we have a pair. And whenever we have one in z, we have a block in x from xn. So those are kind of pins, and it pins the blocks from xn. And using this kind of product space, we can do the estimates for the shifts. So what we get at the end that my pressure function is piecewise linear. So on each of those intervals, it's going to be aligned with the slope Cn and intercept the entropy of my shift. And I made a picture here of it. So you see the entropies of the shifts xn here, and this is sort of your pressure function. It might have a freezing phase transition here if my TNs, for example, converge to some kind of point T, or if there are finitely many of them, or it can kind of continue like this, going to this asymptote. Okay. Yes, right. So my pressure function is always convex and Lipschitz, and the first order phase transitions correspond to non-differentiability points, so we can only have countably many of them. And we do get infinitely many here, so the case of infinitely many is realized. We were extremely happy with this result. We kind of thought we proved everything we can possibly prove about phase transitions. And there was, this was all during COVID. So there was that conference that Brian was organizing, and I was giving a talk about it first time, and I screwed up my slides. So when there was a typo, which is not unheard of, but this typo was pretty bad. I missed this word increasing. And Ronnie, who is here, caught me on that. I know. So what was his point? Okay, if you have a convex function, it can have a countable dense set of points of non-differentiability. So if you miss this word increasing, and that was exactly Ronnie's question, it may seem like my potential has a dense set of first-order phase transitions. And when Ronnie brought it up, my answer was no, that can't be possible, can it? And next year, we figured out that it can. So if you give me any countable set bounded away from zero, I can find a continuous potential phi on a full shift, which has phase transitions precisely at points of my set S. So we can have dense set of first-order phase transitions for continuous potentials. Okay, so this is actually a corollary of our main result. Our main result is the following. So give me any convex Lipschitz function on the interval alpha infinity, which has a slant asymptote. Then there is a full shift in the continuous potential phi, such that the pressure function of phi coincides with this given function. So this condition is kind of if and only if every convex Lipschitz function with an asymptote is a pressure function for some continuous potential on a shift space. So this result, of course, is much, much stronger than what we had before. So let me remind you what we had before. So before that, we had, we kind of constructed a pressure function that was piecewise linear. And here we had entropies of my shifts xn. And we get a sequence of phase transitions. Now, if you want to have a dense set of phase transitions, I would have to have a kind of a bunch of corners here. So I would have to fill the whole interval with entropies of equilibrium states of those phase transitions. So our first problem was to even find the shifts that fill up whose entropies fill up the whole kind of interval. And we picked beta shifts for that. And that was the point where I switched from beta being the temperature to T being the temperature. I don't think I'm... so that was much harder to do. Anyway...
This restriction in alpha, do you think is a technical issue, or do you think there's something?
Oh, no, this is absolutely not technical issue. We need to have it. So the pressure function, it crosses at zero. It has to be the topological entropy of the shift. So once I move out of zero, I can basically do anything. But if I include kind of point zero here, it restricts me in terms of what shift I can get. In fact, for full shifts, I will know exactly which full shift it is. And that's not, I can't do anything with that.
But if I had a convex function that takes the value log 2, for example, at 0, do you realize?
I cannot do that, yeah. We don't have enough room for doing it like on one particular shift. We need one, like I can do it on a shift of log of 3 symbols, so entropy log 3, but not log 2. I need a bit more for the construction.
You can realize any convex?
I can realize any convex function at all on a whole line if you don't restrict me to full shifts. So if you tell me, okay, pick whatever shift you want, I can do it. But if you want a full shift, right, I kind of need like, I need one more dimension, otherwise it's 2. So if you have a function, you see this last kind of supporting line here, it crosses here. So if it crosses at log 2, I need a shift of log 3, the full shift. So if it crosses anywhere before log 3, I would be fine. But if it crosses exactly, it's not enough room. I need room. Okay. So I don't know if you kind of can actually realize it precisely for one particular shift. Yes. Okay. So there were a lot of problems with that in terms of the construction. For example, these guys are no longer disjoint, you cannot define them to be some constants, there are uncountably many of them, so there are tons of problems here, but once you overcome that all those problems, you get a lot. First of all, we know now that there are no restrictions on possible number of frequency of first order phase transitions, anything can happen. 2, you can also have any higher order phase transitions because you just come up with a convex function which has whatever differentiability assumptions you want on it, and here you go. Here's your phase transitions of higher order. We also know that we can do any shape of the pressure function after the phase transition, well, as long as it is convex. So here's the answers for the first three questions that I posed. There is a huge dichotomy in one-dimensional case. For Hölder potentials, you have no phase transitions at all. Everything is analytic and nice. And for continuous potentials, you have all these pathological situations. Kind of anything is possible. Yes. So the question I haven't answered yet is about an analytic pressure function with multiple equilibrium states, and I can answer that one as well. We have a theorem for that. Let me do the theorem. So if you give me a strictly convex differentiable function, could be analytic if you like, with a slant asymptote, that has to happen. And you take any upper semi-continuous function with values in with integer values, can be infinity as well. Then I can give you a full shift on a finite alphabet and a continuous potential, which would have that function as a pressure function, and the cardinality of the set of ergodic equilibrium states for T phi is exactly n of t. So you basically can change the cardinality of your ergodic equilibrium states at will. You can have two of them here, and then infinitely many there, and then go back to uniqueness, something like that. So regularity of the pressure function has no effect at all on the number of equilibrium states which is possible. Okay, but everything I've talked about so far, we kind of were very focused on phenomena that we wanted to obtain in terms of phase transitions, and we didn't care at all about our choice of shifts, our choice of potentials, our choice of equilibrium states. So an interesting question would be, could we specify equilibrium states at phase transition? So let's say I would like to have a first order phase transition, but I would like to have my equilibrium states at that transition be these particular measures. Can I do that? And that I don't know, but a very related question to that is freezing phase transition, because you do care about the support of your ground state. You want to specify the support of the ground states that you have at the end. So this is kind of one aspect of the question I put on. Okay, so let me tell you again my understanding of the freezing phase transition in one dimension. So as before, we have a shift space and a continuous potential, and we are interested in the behavior of the pressure function when my T goes to infinity, which means that my pressure, my temperature is lowered to 0. So Jean René explained very nicely how we get ground states. So we look at weak star accumulation points of equilibrium states of potential T phi. So potential T phi does not have to have a unique equilibrium states, but we can kind of pick one and look at the accumulation points. And those are the ground states of phi. And we know that the ground states in general are not unique, even if you take Hölder potentials on a full shift. But that's not a problem, because they all have the same free energy. Remember, so if you have a ground state, then it must maximize this integral. Right? This is that folklore theorem that you stated. And the entropy must be maximal as well among all the entropies of the measures which maximize the integral. So if you look at the pressure function at T, right, and you pick equilibrium state of the potential T phi, it has to be equal to this. And for large T's, right, it will be close to the free energy of the ground state at temperature T. So this thing is the asymptote of the pressure. So my potential has a freezing phase transition if the pressure function reaches its asymptote at a finite temperature value. So we want to look at a full shift, one or two-sided, and Y would be a proper subshift. And the question we consider is which continuous potential on X has a freezing phase transition at some temperature T0, and the ground states being precisely the measures of maximal entropy of Y. Okay. So again, my pressure function is going to look like this. There is something happening before this value T0, and at T0 it freezes, and this is where the topological entropy of Y is, and the ground states here, so the equilibrium states here, would be the measures of maximal entropy of Y. Okay, so we can construct such a potential. What do we want from it? So we want it to be zero on, this zero is not important, any constant is fine. But let's say we want it to be zero on Y and then drop off from Y. So this is a Hofbauer type. Zero here goes down here. We want the pressure of phi to be exactly the entropy of Y. This would mean that my phase transition happens somewhere before 1. Again, it doesn't matter when it happens, we can scale. And the most important part, we want the set of equilibrium states for phi be exactly the set of measures of maximal entropy for Y. If we have these three things, we have a freezing phase transition on Y. Okay, so there are several different methods of getting such a potential. First of all, there is a very general existence result. So this is a joint work with Dan Thompson. So for any compact topological dynamical system with positive entropy, we want, of course, the entropy map to be upper semi-continuous, otherwise we can't have, equilibrium states may not be there. Okay, we pick any kind of closed invariant subset, and then there exists a continuous potential on X which satisfies those three properties. So we can get a freezing phase transition for some potential. It exists. So this is an existence result. It's, the proof is based on Israel's theorem. In particular, it tells us absolutely nothing about what type of potential can do it, right? We know it's there, but we don't know what it is. We can say much more if we specify what my dynamical system is. So if X is a two-sided full shift, and y is any subsheet of x, we can define my potential in this way. So it is 0 on y, and then we have some kind of values, right, depending on the distance. For the through-most shift, you had here 1 over n. So again, exactly the same construction. My aj should be an increasing sequence of negative numbers. Then I can tell you exactly which aj would work, right? And this works for any shift. By exactly, I don't mean exactly, but what did I say? Yeah, so everything is fine. It's continuous. It vanishes on y. It is negative of y. So all we want is the other two properties. So if you pick aj to be this, so nj here is the number of words of length j in y, and then you have this kind of term here that it's not clear like how. So this is the fastest growing term, kind of, and then some little extra which doesn't really matter. So if you have a sequence which is like that, or anything less than this, you get a phase transition. So this gives you a range of potentials which would generate a phase transition on y. And it works for any subshift. On two-sided shift. So the methods we use are the same that we did before. We use those pinning sequences, and it does not generalize to one-sided case. We do have some technique for one-sided case, but then my sequences aj is kind of not like less optimal. So the faster it decays, the easier it is for you to have a phase transition, freeze and phase transition.
So y could be quasicrystal?
Yes, anything you like. And that would be your potential for the freeze and phase transition. There is a question of optimality, right? For example, if you take any sequence, you know that if you take any sequence which is less than that, decay increases, decays faster than this, then you get a freeze and phase transition. But if you take anything that decays slower, would you get it or not? Well, at some point you will not, right? But where is this threshold? Okay, and for one-sided full shift, we can also get similarly, like close to optimal sequence, but only for subshifts of finite type, and this is work with Dan. So again, we are trying to construct potential which satisfies those properties, and the question is, what is your sequence? So the sequence that we came up with is something like that. You see this term is here, it has to be here. I think you cannot get rid of this term. So this is the number of words of length k. And this is something extra. So this is like how much slower it has to decay. You see the terms that j over log j is no longer there, which was the fastest term. So this is kind of better than before, but it only works for subshifts of finite type. Yeah, okay. These techniques are kind of more in line with the ones of Hofbauer and Lopez, and not the pin sequence techniques. Oh, and apparently I'm done.